All right, here's our next lesson, and yet I am trying yet another different method of recording this. This is the third thing, or software that I'm trying. So let's hope this works. Let me know how it is, the video quality, if anything weird's happening, like the writing is backwards again, okay? And I'm hoping this turns out to be the best of the three so far, but we work things through step by step. Our next lesson is on electric potential energy, electric potential. There's going to be a lot of terms in this lesson. We've heard some of these terms before in grade 9, but I'm going to try and explain what each and every one is. So the content is a little heavy. Math, not too bad. Content, a little heavy. So let's go through this PowerPoint. That didn't change. How do I go to the next slide? All right. So again, I'm going to compare this with gravitational energy. So if you remember when we did gravitational potential energy, in general, we had this formula here. I don't know if you can see my mouse, but I'm circling gravitational potential energy. Now, for gravitational potential energy, it was always negative because you were stuck, you were bound towards something in that gravitational well. For electric potential energy, it could be negative or it could be positive. That depends. Right? If you are bound to something or attracted to something, then it's negative. But if you're being pushed away from something, then it's positive. You'll have to determine what's happening with the charges and if you're being attracted or pushed away. And so it'll be you who determines whether or not the sign is positive or negative. Right? The equation's not going to magically spit that out for you. Okay. Next, electric potential. Electric potential is different from electric potential energy. Now, I think I've told you before I don't like the word potential energy. Consider it as stored energy. It's energy that's actually there, but it's stored. Potential is a much better word for this. Now, if you were to take an amount of energy, and look at it as how much energy is available for any given charge, then you have a certain amount of potential. So we call the electric potential as the electric potential energy for every unit charge. Right? And we give it the symbol V. And this you've seen before, because V is measured in volts, if you remember from grade 9. Sorry, I just have a couple distractions here. This is one of them. This is Joko. Hold on. Here's the other one. They're just curious to see what I'm doing. This is Beanie. I'm just going to pause for a minute, take care of them. Okay, so let me try and explain this again, because it is quite confusing. I'm going to make this a little bigger. We're going to go to the whiteboard. There we go. All right. So, electric potential energy. You have the equation for electric potential energy, and in the equation you have two charges, Q1 and Q2. So let's take one charge here, positive, one charge here, negative. They're opposite charges, they attract. You can determine the energy involved in that system. If I make this positive, right, they are like charges, they repel. Now we have a positive potential energy, and it's going to be pushed away. Well, technically they're both going to be pushed away. But if we were to hold this one in place, then that would be pushed away with however amount of energy. Okay? Now, if I were to remove this and look at this point, at that point, there's a certain potential. It's almost like a field, but a field represents numbers everywhere, and if you were to place an object with properties of that field at that point, it would feel a force. Whereas potential, again, you can think of it as numbers throughout space. And at that point, if you were to place a charge in that point, it would have energy. Without that charge, there exists a certain potential. This is why I like the word potential used for electric potential, because you can really think of it as the potential for energy. Whereas potential energy is better to think of as a stored energy, because that can easily be converted to kinetic as it gets shot away. Okay, so that's the difference between electric potential energy and electric potential. Okay, let's get back to the PowerPoint. All right, so if you write it as an equation, potential is given the symbol V. It's measured in volts. Energy, of course, is always measured in joules. And we write it as, just as its definition, the electric potential energy per charge. So we divide it by Q. Okay, moving on. So we know that potential is the amount of potential energy per charge. So if we were to substitute our equation for potential energy, which is K, Q, Q, different Q's, over R, over Q, one of the Q's cancel. And we're left with KQ over R. That Q1 would be this charge. And R would be the distance between that charge and a point in space. Okay, and K we know is Coulomb's constant. This also tells you the units of what a volt actually is, which we never did in grade 9. It is 1 joule per coulomb. Okay, moving on. All right, very important to note, these are all scalar quantities. Energy is a scalar quantity, we know that, but potential is also a scalar quantity. And it can be both positive and negative, just like energy can be both positive and negative. And we have a rule for how we determine that. So basically, it's quite simple. If you have a positive charge, right here, let's go back here. If you have a positive charge, the potential at any point will also be positive. If you have a negative charge, the potential at any point will be negative. So in this case, if you're trying to solve this equation, and you're given a certain charge, whether it be positive or negative, you can put that positive or negative into the equation and it'll work out, right? But you can only do that because it's not a vector equation. Remember, the sign for charge does not determine direction. Okay, moving on. That's just like what I said. Positive charge, positive potential. Negative charge, negative potential. All right, electric potential difference, yet another term. Just move this. All right, so electric potential difference is the change in electric potential. And why do we not call it the change in electric potential? I don't know. Right? Just like I don't know why we don't call displacement as change in position. Right? But yes, it is change in potential. We call it electric potential difference, and it is delta V. The V is capital. It's very important. Right? It's not a lowercase v, that's velocity. And yes, we will have equations that have both potential and velocity in the same equation. So be very, very clear when you write a capital V or a lowercase v. Now, since it's not a vector, the path we take doesn't matter. If there's a certain potential here and a certain potential here, how you get from here to here doesn't matter. You can go like this, you can go a straight line, or come back around and then come here. It doesn't matter. Right? The potential difference will still be the same. Now we can write this as a change in energy, and that'll be the work done. Okay, so to take, let's say, this charge Q from this point A over to point B inside of an electric field. So because we're inside of electric field, there'll be a certain potential at A and a certain potential at B. And if we take a charge and put it at A, it'll have a certain amount of potential energy. And if we move it from A 2b, its potential energy will change and will have done work on the system. Because its potential energy has changed, its potential has changed, and you can play with the equations a little bit here to say that the change in potential energy equals the change in potential multiplied by that charge that we moved. Okay? Moving on. Hold on. Where? Here we go. We talked about the signs. Okay. Back to parallel plates. I told you parallel plates are important. We're going to be using them a lot. Okay, so here we have two parallel plates. And of course there's a charge on each plate, and therefore there is some constant electric field between the plates. And the plates are separated by some distance r. In this case, when we use the term r, we're talking about the separation between the plates. Be very, very careful. Let me just make this big. So we've learned a couple equations. If you're dealing with point charges, like this charge and this charge, you might want to use, depending what I ask you, some sort of equation to calculate potential energy as K, Q1, Q2 over R. In this case, R is talking about the distance between the two charges. However, if I'm talking about parallel plates, we call the separation between the plates R. Yes, you can see them in different equations, and yes, you should know which R we're talking about. Okay, I've seen many students try and get them confused. Don't try and do that. Okay, back to the PowerPoint. So we have a charge Q. It's at one plate, and we want to move it over to the other plate. To move it over to the other plate, we will have to apply a force. The minimum force we'll have to apply must be equal and opposite to the electric force, and we can move it across those parallel plates at a constant velocity. While doing that, we actually do work, and you can calculate the work. Work equals force times displacement times by the cos of the angle between them. In this case, the force you apply and the displacement are parallel in the same direction, so you have an angle of 0, cos of 0 is 1, which is what I have down here. Then you have the force that you applied times the displacement, but in this case I'm writing the displacement as r because that's the separation between the plates. That's how far we're moving the charge. And we also know the force that you apply, F, must be equal to the electric force, Fe. And we can calculate that from what we learned yesterday. The electric force equals Q times the electric field strength, epsilon. So here we have an equation for work done. And we're going to go a little bit further with this. Because we know work done is also equal to the change in energy. And we just learned the change in energy is equal to that charge times the potential difference. So if we set those two equal to each other, charge cancels, and we get that the potential difference equals epsilon, the electric field strength between the plates, times by the plate separation. We usually don't write the equation like this. We usually write it as epsilon equals potential difference over the separation between the plates. Why? Because electric field strength is hard to measure. Separation between the plates is easy to measure. Grab a ruler. Right? Potential difference is easy to measure. You were using multimeters in grade 9 to measure potential difference in electric circuits. You could do the same thing across the parallel plates. Right? So if you can easily measure those two things, then it's epsilon that you're going to be calculating. It's the electric field strength that you're going to be calculating. Okay? Now notice that I did say that the electric field strength does not depend on R. We learned that in yesterday's lesson. I can move those plates further and closer together, and the electric field strength will not change. This is another thing to be careful of. I could ask you something like, if I were to double R, what happens to epsilon? Nothing. But something does happen to the potential difference between the plates. Okay? Because you would have had to have done more work to move it twice the distance, and there would be a greater potential difference between the plates. So if you double R, you double the potential difference, but epsilon remains the same. Right? Epsilon does not depend on R. The electric field strength does not depend on the separation between the plates. Okay. All right, so let's do some problems. This problem is on the back of your worksheet. Let me make the screen big. We'll go on the whiteboard. All right, so in this problem, we have a 5 microcoulomb charge located at the origin. So we're going to draw a little coordinate system here. And right at the origin, we have a 5 microcoulomb charge. Okay? And a second point charge of minus 2 microcoulombs, so this one's positive, is on the x-axis at a point 30. So minus 2 microcoulombs, and 30 meaning it is 3 meters away. If the potential is taken to be 0 at infinity, which it would be, because if you're an infinite distance away, if r equals infinity, then your potential goes to 0. Find the total, part A, find the total electric potential due to these charges at P, whose coordinates are on the y-axis here. So this is a point. There's no charge there. It's just a point in space. And it is 4 meters away on the y-axis. Now to figure out what the total potential is at P, so the total potential, we are going to have to sum the potentials provided by this point, let's call it A, and this point, let's call it B. So VA plus VB. Now, these are not vector equations, so even though this is two-dimensional, we do not need to use components. We don't care about direction. However, because this is a negative charge, the potential at B will be negative. We don't have to write it as negative. We're still taking the sum. If we want, we can just sub in the negative in with the charge, and that'll take care of itself. But remember, don't do that if it's vectors. Okay, so this is KQA over R, A to P, plus KQB over RB to P. Now RB to P we don't know, but this is a really nice problem. Right? 3, 4, 5. You can double check that with the Pythagorean theorem if you want to, but it's a nice triangle. All right, now we can sub in our numbers. I don't really have much room for that, but just remember that that Q will be negative. So it'll be this term subtract by that term. And if you sub in those numbers, you will get a value of 7,650 volts. So make sure you sub in your numbers. Try to get the same thing I did. For part B, it says how much work does it take to bring a third point charge of 4 microcoulombs from infinity to P. So I take a third charge, right here, third charge. It's all the way over here at infinity. So I'll go over to infinity and I'll bring it, I'll do work on it and bring it all the way to point P. How much work is done? Well, to calculate that, our work equals our change in energy. Okay, and the work is being done by the, by whatever. And our change in energy is our change in electric energy, which we can write as Q times our change in potential. So we have Q, our change in potential is just potential difference, but like I said, it's just change of potential, final potential minus initial potential. Initial potential was all the way at infinity. When it's all the way at infinity, your potential is 0. So we're just left with Q times our final potential. Final potential is what we calculated in part A. And the Q is the charge that we're bringing over to P, which is 4 microcoulombs. Right, so to calculate this, we will have 4 times 10 to the minus 6 coulombs times our potential, 7,650 volts, and we get 3.06 times 10 to the minus 2 joules. All right, so that is the first question. All right, let's move on to the second question. I'm going to erase the first question. I will post these, so don't worry about writing it down, or you can even pause the video. Hopefully the quality is easier to see. Second question says the electric potential at a distance of 25 centimeters from a point charge is minus 6.4 times 10 to the 4 volts. Determine the sign and magnitude of the point charge. Okay, well, if the potential is negative, we know that the actual charge is negative. So the sign you should know right away. Potential is negative, charge is negative. Right? To figure out what the actual magnitude is, we go to our equation, V equals K Q over R, and we just rearrange it to solve for Q, where Q equals V times R over K. Right? Then we substitute our values. Right? I told you the math isn't that hard in this unit. Right? But there's lots of new terminology, and it's all things you really need to visualize, because I'm sure you've never seen a point charge before. I know I haven't. Okay, what's our voltage? Minus 6.4 times 10 to the 4 volts. R is, change it into meters, so 0.25 meters. And K, we know, is 9 times 10 to the 9 times all those terrible units. Right? And we substitute that, we get minus 1.8 times 10 to the minus 6 coulombs, or just minus 1.8 microcoulombs. Negative charge with a magnitude of 1.8 microcoulombs. Not so bad. Last one is parallel plates. Now, this equation is for parallel plates. This equation is for point charges. Okay, make sure you understand where these equations came from and what they're actually describing. Remember, equation says 1,000 words. They describe something in nature. This one is for point charges. I see a lot of students using equations for point charges on parallel plates and equations for parallel plates on point charges. Right? These are the two main problems I can give you: point charges and parallel plates. Some equations do work on both. Some are just for one and not the other. Right, so make sure you go over, if you want, take your formula sheet, go through the lessons, go through the videos, the examples, and label on your formula sheets which ones can be used for what. Okay. Alright, so for this one, it's parallel plates. We're not using this equation. And it says, what potential difference would have to be maintained across the plates of a parallel plate apparatus if the plates were 1.2 meters apart? So that's R, your plate separation, to create an electric field strength of 1.5 times 10 to the 4 newtons per coulomb. So that's epsilon. Now for parallel plates, we derived this in the PowerPoint. Epsilon is potential difference over R. Now it has a direction. We're not going to use that though. But you can determine that. You would need to know which plate is positive and which plate is negative. So rearranging, we get potential difference equals epsilon times R, and we're just substituting and using our calculator at this point. It's not too bad. 1.5 times 10 to the 4 newtons per coulomb times R, put it in meters, 0.012 meters. Multiply them and you get 180 volts. Okay. Hopefully you're okay with the video. Hopefully the quality's good, the content's good. If you have questions, make sure to ask me. Hopefully the writing isn't backwards. And let me just see if I've missed anything. No. Okay, so I'll see you for the next lesson. Well, I won't see you, but you'll see me.